Hello, students and parents. Welcome to another session from Concept Clarity. Today's session is about graphs. We are going to continue our discussion on graphs. In the previous session, we saw how the displacement time graph can be used to then find the velocity time graph. And from the displacement time graph, we can also find the acceleration time graph. If you have not watched the video, please do watch that video before you get onto the reverse, right? Today we're going to see the reverse process of converting velocity time graph into displacement time graph. This is velocity time graph to displacement time graph. So let's begin. We'll take the same graph. This was the velocity time graph which we had seen in the previous session. Velocity time, and then now we need to get the displacement time graph x t, right? So let us start with the first slipping line. The slipping line, for the slipping line, the velocity time graph, velocity is 0. But we know that velocity is equal to change in displacement by change in time. So this can mean now 0 is velocity, so change in displacement is equal to 0. It's not the position but the change in displacement. So change in displacement can be shown 0 here. Okay. Now the second part. Second part is the slanting line. The slanting line. In the slanting line, we know that velocity is increasing. This shows that velocity is increasing. With variation in time, velocity is increasing. Does it mean that displacement is also increasing with time? Let us find it out. So velocity is increasing, and we know that velocity is equal to change in displacement by change in time. So we can write this, we can denote this as dx is equal to v dt, right? So I need to know displacement. So how will I find out displacement from this equation? I need to integrate both sides. I integrate both sides. So for x, for dx it will be x1 to x2. And we know clearly that x1 is this position here. This is x1 when it is 0. And we want to know from here, this is the starting point for point 2 and this is the ending point. So but for the starting point x1 is actually 0, right? This is 0. And the variant here is dt. So we need to know from time 1 to time 2. Okay. I will say this is time 1 to time 2. So how will I get the graph? How will I get displacement? So it is clearly visible here that if I want to know, if I have to do this integration, I'll have to find the area of this particular triangle, which is a right angle triangle. So if I need to find the area of this right angle triangle, what I need to do? Here first I'll do x2, x2 minus 0 because x1 is 0, which is equal to the area of area under the curve, right? Area under this curve. So to find the area on the curve, we know that to find this area, it is equal to the area of the right angle triangle. So it will be half V. I can write it V, or I can write it just to show the calculation in detail. We'll assume that this is V2, this is V2, and this is V1 here. So I can say V2 minus V1 and change in time. That means I'll get T2 minus T1. From here, I know that V1 is actually 0. V1 is 0. So I'll get X2 is equal to half V2 delta T. I can say T2 minus T1 is delta T. And we also know that X1 is 0 and V1 is 0. right? Because we're starting from this point. V1 is this point where it is 0. And we know x1 is also 0 for that particular position, for that particular velocity. So now that we have got this, we know here that x2 is varying as a result of product of v2 and change in time. But we got here that x2 is half of v2 delta t. x2 is half of v2 delta t. This is for this entire triangle. This is for this entire triangle. Now let me say if I want another position, let me take another position here. And this position here, let us call it, this is v3. For this v3 position, if it is exactly at the center, exactly at the center of the line, the velocity will be v by 2, right? V by 2 means v2 by v2, v2 by 2. I'll write it clearly again. This point here, velocity is v2 by 2, half the distance. So now if I want to find the displacement at v3, which I assume is v3, but basically it is v2 by 2. So I find x3 is equal to, it will be the same area under the curve, right? It will be half v3 delta t. And what is v3 delta 3? v3 is actually v2 by 2, and delta t is half delta t by 2, right? For this triangle, this is halfway. I've taken delta t, I've taken delta t by 2 here, right? So you can notice here that x3 will become 1/4 of x2, right? x3 will become 1/4 of x2. I would have expected if it was directly related, it should have become half of x2, which is not the case. So then we can say this is a non-linear relation. It's a non-linear relation. So I can draw it like a curve. Okay. Now the third part. This is the third part. The third part says that velocity is a constant. So I can write this equivalently as dx by dt is a constant, and that constant is v. Now I need to find out displacement. I need to find out the displacement. So what I do? I say dx is equal to v dt. But here v is a constant here. V is a constant. So if I integrate both sides now, if I integrate both sides, I'll get delta x is equal to v is a constant can come out of the integration and delta t, right? So what is the average velocity? Average velocity is delta x by delta t. And delta x is v delta t divided by delta t. This will go to become equal to v. So that means it it clearly says that change in displacement is constant time change in time. That means as time changes, displacement changes as a multiple of constant velocity into the time. So it has to be a straight line. It has to be a straight line. I hope you understand the concept that why it should be a straight line. If I take it as an example, I'll take an example here. So I'll say delta x is v time, and I'll say v is some constant number 2, and t is changing here, right? T is changing. So what will happen to x? X will have many displacement. X2 will become for let us assume this is starting from let us assume that this is starting from 5. So xa will become 5 into 2, 10. Then at 6, come 6 into 2, 12. As you can see, it is linearly changing, right? After 12, 6, 7 will become 14. So we can see clearly that it's changing as a linear fashion, okay, because V is constant. Then similarly, you can plot the other portion of the graph, which is the curved and then is curved and straight. Remember that displacement, you have to continue from this particular point. And at this point, we know that displacement is V delta t. So V delta t is here, right? From V delta t, then you can take the displacement. And then here finally, there is no change in displacement, which is shown here as no change in displacement. That means delta x, even at this position, if I take delta x, if I plot x here, I get x1 and x2, both are equal. So x2 minus x1 becomes 0. So that's why there is no change. I hope this is clear. I hope you have understood how to get velocity time graph from displacement time graph. I guess there's nothing much to summarize in this particular session, but in the next session, we'll take up how to get the displacement time graph from acceleration time graph. So stay tuned, subscribe, like, and share. Bye.